Hey guys, it's Mr. Sheelan here. So this is going to be a video that's pretty much going to cover like the vector walkthrough, vector demo, vector, what other words can I use? Basically, this is going to be the lecture, like a video lecture of what we're going to be doing in class, just in case that you miss it, just in case you're not in class or you need to go back and maybe watch this if you forget something or if the notes aren't good enough. You know, if there's something I missed in the notes. Okay. So the way I'm going to be doing this, though, is that I'm going to be walking through with you guys how it is that we use vectors, why we use vectors, and what things we need to have when we're showing or using vectors. So we've already seen a little bit. If you watch or when you watch the video for the notes, you saw how we use vectors a little bit. You know, at least you know the anatomy of it. You know that it's basically just an arrow, but there are some, you know, limitations. There are some, I guess, rules, if you want to call them that we should follow. So in order to kind of show you guys what we're going to be doing, I'm going to go through some of the check your understandings to kind of show you, to walk through with you, you know, what it is that we're looking for when we're making vectors. And for the most part, it's pretty straightforward. Now, as far as how I teach, you know, what vectors are like. So, okay, remember. So, as an example, remember, to remind you guys, a vector, for the most part, it's a dot. Okay? It's an arrow. And that's it. Okay? That's a vector. Some applications, some people don't add the dot at the end. They just have the tail and the head. That's how they teach. For me, it is imperative that you have a dot. It is. The dot not only tells you, but it tells the reader, or should tell them, where you're beginning and where you're ending. And more importantly, it serves as a better reference point to when you change directions, a better reference point to know where you start, where you end. And that's especially important when you are working with, you know, it's especially important when you're working with things that may have to be drawn to scale, especially when you're working with, you know, let's say more than one vector, or more than, let's say, 3 vectors, because things can get a little complicated, okay? So, now when we are making these vectors, okay, they can be just like this. They can be a quick, hand-drawn little dude that for the most part isn't to scale, that just is, you know, relatively speaking, a fair representation of whatever, you know, vector quantity you're trying to show. Now, in some cases that's fine. In other cases, not so much. Okay, so where would we see where a vector is not drawn properly? So let's say this is an example where this would be drawn incorrectly. So let's say this guy right here. Let's say that is 21 meters. Okay, and let's say you walk 21 meters to the east, and then let's say you then changed directions, and then you walked 50 meters to the south. Do you see what the problem is already? Okay. When we are drawing vectors, we have to make sure that even if they're hand-drawn and they're just eyeballs, you know, we're just kind of guessing the length here, you at least have to make sure that the lengths are somewhat proportional to the magnitude of your vector. Okay, because if you do this, and if you try, let's say you try to get the resultant here, if you try to find your displacement, you are going to be quite confused. Okay, or at least your brain for a second is going to be confused, like, oh, how is it that we get this, you know, how did we get this angle when, like, this is 50, your picture will not line up with your data. Okay, your model, this is what this is, your model does not fit your data. And if your model doesn't fit your data, then why should I trust your data? More or less is the argument. So we have to make sure that we include, or sorry, that not that we include, but we maintain this rule of having vectors represent the distance or the magnitude, the velocity, the acceleration that it's projected to have. So for instance, if that's 21, then 50 should come like all the way down to like here. It should be over double of this guy. So if that's it, boom, yeah, it should be like right down to here, out of the camera angle. Okay, should be way down. Okay, so keep that in mind. So another rule, and I kind of did it already, and I'll do it again. Okay. Yeah, if you know that reference, yes, I do listen. I listen to Filthy Frank, and I also do listen to Joji. But anyway, what was I saying? Sorry. So when we're drawing vectors, okay, we start with our starting dot. So that's probably rule number one. So first step, start with dot. Okay. So we start with our dot. And I'm going to zoom in a little bit there just so it's a little easier to see. Okay, so we start with dot. So we start with our dot, and then the next thing we're going to do is we're going to extend the tail. We're going to extend the tail. So now when we extend the tail, you can freehand it or you can use a ruler. Okay, I like using rulers quite often because, you know, having a nice and straight vector just makes everyone's life easier, you know. And then the third thing is you are going to place head. You're going to draw the head. Okay, and then you're just going to do that, and it's that simple. Okay, which for the most part I didn't have to walk this through. You should know this, but here's the fourth thing. So if we have a new direction, okay, if we're now moving in a new direction, then the fourth thing is you're going to place new dot on the tip of the previous vector head. So place new dot at the tip of the vector head, which is what we did over here. So we're going to take our pen or pencil here, and the new dot's going to go there, right at the end. And then you're just going to, then the fifth step would be like draw, you know, then repeat. Okay, then 5 would be like repeat. You know, 2 through 3. Okay, and then just draw, boom. And you have two vectors. And we do the same thing with our resultant. So if we walk to the east and then we went south and we want to know what's our displacement, what's the resultant, then we would do the same thing. Now, luckily though, we already have a dot down here, so we just have to kind of line it up. Okay. Right there. And then we would have our resultant. Okay. We'd have our displacement. We'd have our hypotenuse. Okay. So for the most part, it's pretty simple. You know, making vectors is pretty simple. Now, where it can get complicated and where it can get difficult, and arguably so, where this can get difficult, but also something that's so amazing. Again, it's not just about vectors. It's also just the fact of physics. It's like you can draw everything. It's so cool. You can draw these vectors to scale. And you can use trigonometry to solve for them. We're already using trigonometry to solve for them, but what's so cool is if there's like a super complicated problem, if we've got like 5 vectors that look like this, like if they're like crazy vectors, like for instance, if they're like this, and then this, and then this, that can get pretty complicated. Like, you tell me, you know, what's the best way to find your resultant? There is a way, by the way. But it's difficult, okay? Because you have to break each one down into a triangle, and then you got to use trigonometry in order to solve for it. And again, we will get to do that. We are going to do that. Not so much with something as complicated as this, but not too far from it. Okay, and I think actually one of them is in here in the Check Your Understandings, which we'll take a look at. But anyway, so drawing things to scale can super duper help us when drawing these. Now I'm not going to go through with you on here just because this is too small. But understand, like on the paper it's just too small. But understand, maybe I can actually do one problem. Maybe I can do, no, actually we're going to do that with number 3. I'll show you that with number 3. so let's draw it to scale. Okay, and I guarantee you, I'm going to answer this problem correctly this time. I apologize for the video, the lecture video where I don't, but we're going to draw this to scale. Okay, so instead of 26, we're going to keep it 26, but I'm going to do this. I'm going to say 26 meters is equal to 2.6 centimeters, and then 36 meters is equal to 3.6 centimeters. Okay, so we're going to do that. So, okay, so he went up north. He paddled 26 meters north. So let's see. Oh boy. Of course. So I gotta do this kind of in a weird way. So let's say I'm gonna start right here. There's my starting point. I'm using my ruler, lining it up just right. We're gonna go to 2.6. That's 2.6 right there. Okay. So that's 2.6 to the center of my dot. Okay, that's 2.6. And now we're going to go 3.6 to the east. So then we're going to put a dot there. Now, of course, just due to human error, like as accurate as you can make these, you can make these pretty accurate. Like you can just use, triangles like this, 2-scale triangles like this, and you can do a lot of damage with it. There are some limitations though. Like for instance, is this exactly 2.6? Arguably, probably not. I'm off somewhere by just a little bit. It's probably 2.5, 2.5, 6, 7, 8, 8, 9, centimeters, whatever the actual true measurement is, down to the last molecule, down to the last atom. That's present. That's human error. But it can get you super close to what it actually would be. Okay, so they traveled, so this right here, we better put our compass up here. Our itty bitty little teeny tiny compass. So north, south, east, and west. And west. So here on this guy, they went. We'll do this. So that's my displacement displacement y. Sorry, displacement y because it's north, and it's 26 meters north. And then our displacement for our x. I almost did it. You saw me. I almost did it. Is 36 meters east. Okay. And then we're trying to find the displacement. What is our displacement? Okay. What is our displacement here? Okay. Now when you're for yourself, when you're drawing vectors, and especially when you're labeling your vectors, like doing what I just did right here is actually pretty important. Here, I'm zooming in on this real quick just so you can see it a little bit better. Okay. Let's see. Sorry, let's see here. Okay. Now I'm going to reshuffle this a little bit. So what I did is that I said, like, here's the displacement, because that's what this is. This is displacement. And you do the same, I would argue you should do the same thing for velocity. If you've got velocity, you should put like y or x, okay, at the very least, or depending upon your triangle, of course. In this case, it's way easier, but you can put y and x there because it's north-south. It's pretty close to xy. So, okay, now, so this is the direction. So this individual decided to move in this direction. They paddled as hard as they could to the north, but this against the current, or I guess perpendicular to the current, and it carried the kayak 36 meters to the east. So as they were trying to cut north, it did this. It did this number. It went like this, just like our picture shows. So we want to know, what's that displacement? Okay, what's that displacement? And what is this guy right here? What is that? What's theta here? Okay, that's what we're trying to find. Okay, and again, what I'm showing here is I'm just showing like how we can draw this and how we proportionally and how we can use actual measurements to more or less just show like what this would look like. Because again, this is 2.6 centimeters, this is 3.6 centimeters. And you can get the idea of, oh, that's shorter than this. Oh, so this is, oh, okay, that's what I would see like on a map. That's what I would see on a model. That's what I should see, relatively speaking, what it would look like in real life. Okay? If you were like, say, at the river watching this bozo go down the river. Okay. So I'm going to just walk through you guys just because I messed up. Sorry for the bell. Why don't I walk through with you guys on how to, and another bell is going to be coming up here in about 5 minutes. But anyway, I'm going to walk through with you guys how you then use this to solve for it, which I already did, but here I'll do it even better since I messed up on it online, or on the other video, sorry, on the notes. So for, let's see, we're trying to find displacement. So again, you could just use Pythagorean's theorem to find this guy. And if you use Pythagorean's theorem, because I didn't do it online, if you do 26 squared plus 36 squared equals 1972. So square root of 1972, that's going to give us 44.4. So you could have that answer. So with, I'm just going to put over here PT, Pythagorean's theorem. Using that guy, we got displacement equaling 44, we'll just keep sig figs in this case, 44 meters, okay? And we'll see if we get that. We're gonna use tangent here. So remember tangent of theta, which we don't know yet. Or sorry, we're gonna use tangent to find theta first, my bad, is going to be opposite over adjacent. So, let's see. Sorry, 1 second, guys. Perfect. Thanks, sir. So, all right. Sorry about that. Okay. So, tangent of theta is equal to opposite over adjacent. And I lost my pen. Okay, so we just put this in. And remember, to get theta, we have to use inverse tangent. Okay, and remember, make sure your calculator is set to degrees. Let's see if I can get this. Where's the shadow at? Oh my goodness. Nope, that's the camera. Yikes. Oh my god. Here, I'm going to do this. So to change the mode, we want to make sure that this guy is in degrees. Oh my goodness. So you're going to click mode here. Gosh, it's so bright. You're going to click mode right there. Okay. And then I know you can't really see it all that well, but you're going to come down here and it says degree, and you want to just use your arrow keys, go to degree, hit enter, and then just hit like clear. Okay, because we need to have this guy in degrees. So inverse tangent, and on the inside, we're going to have opposite over adjacent, so it's going to be 36, not 26, over 36 over 26, not the other way around. And our theta is going to be still 54. So our angle's still the same. So I guess I did that right. So the angle in here is 54. 54 degrees. Okay. Now, because this is the direction that he traveled, this is the angle we want. Now, you can make an argument for a different angle, and I'll get to that in just a second when we have our final, 44, when we solve that. Because now that we've got this guy, we can solve for this. So, let's solve for him using that. So we could use opposite over hypotenuse. So that would be sine. So it'd be so. That's going to be sine of theta is equal to our opposite over hypotenuse. So that's going to be sine of 54 equal to our opposite, which is 36. And then our, what's it called? Hypotenuse or displacement. Okay. Again, we can just switch them. So then it's going to be, let's see, it'll be 36 divided by the sine of 54. Okay, and what you should get, you still should get, now the decimal is going to be off a little bit. I think when you use Pythagorean's theorem, this guy's going to be like 44.3. Let me double check on that. let's see. No, actually, it's pretty much spot on. It's pretty much spot on. But sometimes you might get, like, if let's say that if I would have kept, like, a sig fig, or sorry, 1 decimal place on that 36, or not on 36, but the 54, if I kept sig fig, or if I had decimal places elsewhere, you know, that guy would be a little off from this one. Anyway, we get the same thing. And there's that bell. Sorry about that. So then we get the same thing. So we have our displacement here equaling 44 meters. Okay, and we get the sense that, oh yeah, this is 44 meters. And then for the piece de resistance, we can then measure how far this guy is. And if you look, I know it's kind of hard to see, but from my angle, I can see that this is pretty much spot on 4.4 centimeters. Okay, so meaning I could have skipped all this math here if I draw something to scale. If I make consistent measurements, I could make a pretty good guesstimation that, oh, the answer should be 4.4 centimeters. And if it's 4.4 centimeters, and every in my pretty much my conversion is every what is that? Every 10 meters is a centimeter. That's what I did here. Then if that's true, my measurement should be 44.4. And it looks like that's actually like super close, because it is like right between 4.4 and 4.5 here on my ruler. Like, it's pretty close. So, and that's what I saw, in the decimal. That's what I saw in my calculations. So that's why, like, again, that's why what's so cool about drawing things to scale is that you can pretty much ignore, well, at least to a certain extent, you can at least get an estimation and expect, like, oh, I should see something, like in this case, I should see something like 44. And then you run through your calculations, and boom, if you get 44, like, oh, perfect, that's exactly right. Okay. Let's just do another one, practice this again, and then we'll call it a day. So after leaving the huddle, a receiver on the football team runs 8.5 meters east, waiting for the ball to be snapped, and he turns abruptly and runs 12 meters south, suddenly changing directions, catches the ball, catches a pass, runs 13.5 meters west before being tackled. If the entire motion takes 7 seconds, determine the receiver. So remember, when we're finding average speed and average velocity, we've got to take the time of the entire event, and the entire event was 7 seconds. Okay. The only difference is that speed uses all distance. So this one's fairly simple. For velocity, however, uses displacement. And I'm going to show you how drawing this to scale can, again, help you tremendously answer these questions. Okay. So let's just now draw this, and we're going to do the same thing up here for the most part. Only differences, so this is going to be trickier. Okay, so just be careful with this, because I can't go 8.5. I could, I just don't. I guess I could. I can make this. I can do a different spot. So I'm going to draw this to scale on a different piece of paper here. So, and let me zoom out just a smidgen. Okay. I know it's good with the glare. It's going to be difficult to see precisely what I'm doing, but bear with me here. So we're going to start right here. Actually, we're going to start. Yeah, about right there. Start there. And we're going to go to 8.5 centimeters. So 8.5 meters is equal to 8.5 centimeters, making a pretty much direct comparison. Okay. And then, so that's east, waiting for the ball to be snapped, and then runs 12 centimeters south. So it runs 12 centimeters south. And I'm using the edge of my page here to kind of gauge, equal distance, so that I've got it'll be pretty good. Obviously, this is because if you were drawing to scale, you would have to measure every little thing, so everything's square. Everything is plumb, everything looks good. So there's 12. And I better write these in. So here we're gonna say this is D1, displacement 1 is going to be equal to 8.5 meters east. Okay, and then this is going to be 12 meters south. And then he runs 13.5 meters west. Okay. Here, and I'm trying to make things nice and square and look good. So 13.5 meters west. I was a little high on that, but it's not the end of the world. Okay, so this is displacement 2. This is going to be displacement 3. And this is 13.5 meters west before being tackled. Okay, so this took an entire 7 seconds. So here is what it looks like, for the most part, to scale using a ruler. This is what he did on the field. So first, before we get into doing that for velocity, let's just get average speed out of the way. So because average speed just uses distance, we can just add up all the distances he ran. So he ran 8.5 plus 12.0 plus 13.5 meters. Okay, and that's going to give us 8.5 plus 12 plus 13.5. That's going to give us a total of 34 meters. So we have a distance of 34 meters. Did it in 7 seconds. So then our average speed here, easy peasy, d over t. And it looks like he ran 34 meters in 7 seconds. And that's going to give us an average speed of 4.8 meters per second. Okay, not too challenging, right? Now that's because it uses all the distance. Every single, even, because remember, distance doesn't care about changing direction. All it cares about is how far did you go? Truthfully, from beginning to end, how far did you go? Every step between. Velocity, though, only uses displacement. So remember, displacement only cares about where we start and where we end. So that means that we only care about where we start and where we end. So that means that we can get a good estimation here of our resultant, which our resultant is going to be from here to here. Okay. I'm going to draw that bad boy. Oop, my hand will stop shaking. And this is what we're looking for. We are looking for this guy. Okay. What is our displacement? So there's a number of ways that we can do this. Easiest way is you make a right triangle. And how would we make that right triangle? Well, we would do this. Now let's see. Best way to do it is that because we know we can just make a right triangle down straight right here, because we know this is 8.5 right here, all we got to do is take our ruler, and we measure 8.5 from this guy over here. Make that mark. And we draw our line there, and then boom, we can now solve everything using, and I know that looks a little off. That's pretty much, it should be pretty plumb. That should be pretty straight. So, but anyway, now we've broken this down, and we know the elements of this triangle. So we know that the distance here, that distance, our y here, is 12 meters. Okay. And we know down here, we know what we can get here. All you got to do, it's 8.5 minus 13.5. What is that going to be? Well, our x is going to be 5 meters. Okay. Now, this is where it can get a little tricky. So when we are drawing our vectors, doesn't matter if we're drawing this to scale or not, but now we've got to figure out, okay, where or what angle do we use? Do we use this angle or do we use this angle? Well, it depends upon our reference. Where did we start? Because remember, we care about where we started and where we ended. So if we care about where we started and where we ended, our theta that we want to find is going to be right here. Because we want to tell, displacement is what's the relationship between the starting position and the ending position. Excuse me. And and the way we go from starting to end is going to be, well, we started up here, and it looks like, in this case, we went west of south by some degree. Okay? So we can find that. So we've got our x, we got our y, or sorry, we got our x and we got our y. Let's find our theta, and we use tangent. So tangent of theta is going to be equal to opposite over adjacent. Our x over y in this case. And then I'm going to then solve for theta. So it's going to be inverse tangent. It's going to be inverse tangent over 5, or 5 over 12. Okay. And that's going to give us 5 over 12. That's going to give us 22, let's go 23 degrees. So theta here is equal to 23 degrees. Okay. Now, we've got theta. Before we can either, because remember, we can use Pythagorean's theorem, or we can use, cosine, or we can use sine to find our displacement. Let's just see what our ruler says. So lining this up, let's see. Sorry, I got to really look in there. Make sure I'm lined up. So it looks like I get something like 13.1. So my displacement should be 13.1, somewhere in that ballpark. So from ruler, I'll write up here, from ruler, should be 13.1 meters is what I should have. Let's see if that's what we get. So let's use Pythagorean's theorem real quick. So 12 squared plus 5 squared is going to give me 169. Then 169, the square root of 169, I get 13. So PT gives me 13 meters. Okay. Well, let's try just, because we've got this, let's just do opposite over hypotenuse. So let's use cosine. So that'd be co. This is TOA, sorry. That's TOA. Let's use co. So cosine of theta is equal to opposite over hypotenuse. So because this is where theta is at, it's going to be 5 over whatever our hypotenuse is. Okay. Again, we can just switch these guys, so then it'll be h is equal to opposite, which, God bless, which in this case is going to be 5, and then cosine of 23. And then our hypotenuse is going to be, so that's 5 divided by the cosine of 23. Ooh, what happened there? What did I do wrong? I'm in degree. Why? Hold on, sorry. Something's not adding right here. What did I do wrong? I'm not getting the right answer, sorry. That's what's happening. Let's see, 8.5 minus 13.5. It's 5. Opposite over hypotenuse. We're trying to find the hypotenuse. Why isn't this working? If you guys have spotted it, good. I don't know why this isn't working. Maybe I didn't hit. So this is what I'm getting so far. I'm getting 5, like 5.43, and it shouldn't be. What am I doing wrong? Sorry for holding you back on this. And if you already saw what's wrong, you can just skip ahead. Actually, after this, it's over. So if you've got the right answer, you're good. I need to figure out what did I do wrong here. That's what I did wrong. This is why it's always good to double check your work. I got my C and my A or S mixed up. So katoa. So it's adjacent. Oh my goodness, it's adjacent over hypotenuse. So it's not going to be 5, it's going to be 12. Jeez. My goodness. So 12, I am so sorry guys. 12 divided by the cosine of 23. And we still get the, okay. Oh, duh, no, that's right. Sorry, I still have 44 on my brain. And I get 13, for the most part, I get 13. I got, in my calculator, I got 13.036. So, but I got 13 meters. So my displacement here is 13 meters. And specifically, now we've got to attach our direction here. So it's going to be 13 meters. So remember, so if this is our compass, so if this is south, if that's true south, this is true north, and this is east, and this is west. This is, I can see that I established where it's sitting, and it's sitting between south and east. Okay, but which lead bearing, which lead direction is it touching? Well, it's touching south. So that means that my angle kind of opens up to the west. So I'm going to say then it's 23 degrees west of south. And then I've got my answer. Okay. All right. So now, if that answer is any way different from what I put on the YouTube video, I gotta double check that real quick. But if it is opposite, if there's anything that's opposite, it's just going to be the answer might include, you know, this angle down here rather than this 23. I'll double check that, you know, after you know, I've closed this and posted this. So if I'm confusing you guys with the direction, I'll clarify that in just a bit, or I guess next time I see you. So anyway, but that's pretty much it. So that's how we make vectors. That's how we can use them and draw them to scale to estimate what our answer would be, and to get a good idea of what we should be looking for. It also helps us kind of visualize, you know, what's happening, because here you could see clearly, like, oh, that's where we can make our triangle, how we can find our measurements, and we can move on. So if you have any other questions, let me know. If not, that's cool. I'll see you guys in the next video.